So today we're going to be learning how you can actually use risk neutral pricing to actually value temperature options. Now, this temperature option is going to be a winter temperature option for the next financial year in Sydney, Australia. Now, if you haven't been watching this series, what we've done is we've actually defined what a weather derivative is, what the contract terms look like. We've then gone through how you can actually model the underlying in the physical probability measure world. We've come up with different SDEs, and the one that we're going to be using in this video is our modified Ornstein-Uhlenbeck process, which accounts for the changing dynamics in temperature over time. Now, what we've also been able to capture is varying volatility. So we have a non-constant volatility where we've been able to describe this volatility using a number of models. And the ones that we're going to choose today is actually the B-spline interpolation. So we're going to combine these things now, and to date, we've actually defined our dynamics for Sydney using the past 180 years of data, but now we're going to take it from the physical probability space, and now we're going to move into risk neutral pricing. So we have two pricing methodologies that we're going to go through in this video. One is going to be our risk neutral pricing approach, actually applied using a Black-Scholes approximation method. Now, the reason we can use Black-Scholes approximation is the fact that during winter periods, the average temperature doesn't often exceed the actual reference temperature, which is 18 degrees. Now, in Sydney, Australia, things do get a bit hotter. We do have outliers, and therefore maybe this approach isn't the best to use. But in European winters and definitely American places in America where we have contracts that are in Chicago and all these other places around the US, in general, the probability of exceeding the average temperature, exceeding this reference temperature, is very low, and therefore you can use this Black-Scholes approximation method. However, failing that, and we're going to see here why it's important to also use a different valuation metric under the risk neutral pricing methodology, and that's going to be Monte Carlo simulation. So without further ado, let's get into it. Now, if you haven't been following this weather derivative series, here's a quick summary of everything we've done to date in only 3 dot points. Now, the aim of the entire series is we're trying to calculate the fair value of a temperature option, but there is some complexity with this. We need to define a stochastic differential equation to describe the temperature dynamics under the physical probability space. Now, we've done this, and we're actually going to be using the modified mean-reverting Ornstein-Uhlenbeck process. Now, we're also going to capture the varying volatility, and this is, again, like I spoke about, the B-spline interpolation, which is capturing our non-constant volatility between seasons. This is the type of contract that we're actually going to be evaluating, except without the cap today. Here we're going to be just looking at the simplistic call temperature option for our degree days, and then put options in the winter period. Now, this alpha constant here is just with every tick, with every degree day in the period, what is our dollar value that we associate with that tick. So here, common values for the US are $2,500 and $5,000. So what does our temperature simulation look like under this modified Ornstein-Uhlenbeck process? Well, essentially it's right here. In this orange line, we have our average temperature that's changing over time. And then in the blue with the stars, we have a simulated price temperature series over time. So this is one simulation path over that given period of time from September 2022 to 2023. So the risk neutral pricing methodology, essentially, because we have an incomplete market and it isn't a very liquid market, the weather derivatives market, and usually OTC, what we're going to have to do to translate our physical probability measure to our risk neutral probability measure is through a market price risk lambda constant. Now, this is going to be, for simplicity, a risk constant that we're defining today. The risk rate is going to be constant in our scenario, and we're going to define that a heating degree day for each degree Celsius pays a unit currency multiplied by that alpha tick rate that we spoke about before. So under the martingale measure now, characterized by this market risk premium, our new dynamic process for temperature actually satisfies the following dynamics under the risk neutral premium. Now, the way that we get this is we apply Gersonov's theorem to our physical probability dynamics, as you can see here. So all we've got now is that our drift term applies this shift of our lambda times by our varying volatility over time. Now, we showed in the last video that by applying the Ito-Doblin to our SDE with our Ito process of temperature dynamics, we actually arrive at the following expectation and variance. Now, the variance formula was easy to calculate because we can just apply Ito isometry principle to our dynamics and we can get our variance. So we have our expectation under the physical probability measure and our variance. But if you remember that it was very important to include our change in average temperature over time. And if we include that, we showed a video where under a certain change of measure, again using Gersonov's theorem, you can actually show that the expectation is exactly that average temperature. So under the martingale measure now Q, what we get is this equation here. And we can actually now define our expectation as the physical probability expectation minus lambda and this integral here, times by this integral here. And similar for variance, our variance is exactly the same. So we have the same variance, but we've got this slight change in the expectation under the risk neutral measure. Now, we're actually going to apply this practically because we have to implement it using Python. So let's take those formulas that we had before with the integrals and let's evaluate it over one interval of time. So for example, we're doing this evaluation, the Monte Carlo method, across days. So the interval is going to be from one day, S, to the next, T. So when you actually evaluate those integrals, you arrive at the following equations for the expectation, the variance, and covariance. So the covariance formula, you just have to do a little bit of Ito calculus for. Essentially, you arrive at this equation here, and this is what we're going to use to actually evaluate our across intervals of constant volatility. So let's look at our temperature option valuation. So method number one is going to be the alternative Black-Scholes approach. First, let's go through the math and then we're going to do the implementation. So the reference temperature is going to be 18 degrees. Our actual contract payoff function is going to be that alpha tick rate multiplied by the difference between the heating degree days minus the strike. Now, this is going to be obviously the difference between this value and 0. So the max of this value or 0. Now the number of heating degree days is going to be the summation of this over time. Now, unfortunately for us, we won't be able to really use this approach very well in Sydney because Sydney often rises during the winter months above the average temperature above 18 degrees. So this really in mathematical terms happens that under the physical probability measure, you can use this approach when you have the probability that it exceeds 18 degrees, approximately equal to 0. So let's see what that means. Essentially, we can use the fact that we've got a Gaussian Ornstein-Uhlenbeck process under the risk neutral measure Q, that it's normally distributed, and we get our mu and then our variance equal to the following. So we've got our temperature that's normally distributed around our mu and our sigma t there. And therefore, what you can actually arrive at is that our heating degree days actually simplifies to 18 times the number of days that we have minus the summation of the temperature over all those single days. So if you actually apply that to the expectation under the risk neutral measure, what you get is that it's approximately, mu is approximately equal to 18 times n minus the summation of the expectation under the risk neutral measure for all the days of the temperature. For the actual variance, what you get is that we just need the variance or the quadratic variation of the temperature process under the risk neutral measure. And essentially what that means is that we take the variance of the temperature and then we have to add 2 times the covariance of this summation across all the different days. Now I'll show you what that looks like in actual practice when we get into the implementation now. So why can't we really use this approach in Australia? Well, like I've just said before, we can see that from our winter period, winter months, from June, July, and August period, our 3-month period there, we don't really have a probability that's close to 0. We've got 3% for this Monte Carlo simulation, 1% there, 3% again, 5%, and you can see that we have the average days we have days where the average temperature does exceed that 18 degree threshold. Whereas if you're in different places around the world where this isn't the case, this is actually a great approach because we get a closed form solution. So now we've got the Black-Scholes approach that we actually have to apply using Python. So let's actually just evaluate this using Python. We are reading in our time array, our volatility array, our average temperature bars, our lambda and kappa. So these are just constants. Now we're going to evaluate this risk neutral integral over each segment of constant volatility. So our time step that we're taking between S and T is just 1 day. So 1 divided by 365.25. Our number of days that we've got is our length of our time array, 92 days in this case for winter in Australia for the 3 months. And then our mean intervals is going to be this particular term here, which is just the volatility array divided by kappa times by 1 minus the exponential of these terms here. So that's just minus kappa times by the difference in time. Now here what we need to do is that we're going to take 18 times the number of days minus the summation of all the average temperatures for over that given period, and then we're going to subtract that value, we're going to subtract the value that we calculated the mean intervals. We're going to take the summation over all the 92 days. Then we take that calculation over and we're going to multiply it by lambda. So we take the summation of the expectation of all of those temperature bars, we minus this adjusted risk neutral parameter times by these parameters here. And then that's calculated as the sum of our mean intervals. And then essentially we take that away from 18 times the number of days. Done. So now for the risk neutral variance. Essentially here we need to use the covariance evaluated over the interval, all of the days, and then the summation of the other days is going to be that m is greater than n, which is the first iteration of days we're going over. So let's evaluate that and what that actually looks like in code. So it's going to be 2 times these terms of the covariance added to the summation of the variance of temperature. So in reality, what variance looks like in covariance on an interval by interval basis is essentially exactly these formulas. So again, we're evaluating the risk neutral integral above for each segment of constant volatility for each day. That's going to be 1 over 365.25. We've got our variance array, which is equal to our volatility array squared, which we're reading in, and then we can calculate our variance intervals. All I'm doing here is I'm taking that volatility squared, I'm dividing by 2 times kappa, and then I'm actually multiplying by 1 minus the exponential of minus 2 kappa times that change in time. Now for the covariance, I'm going to take the sum over all the time array summations. So for the first iteration, I'm going to go over all of the days. And then for the second iteration, so before we had n and m, and here I'm using I and j, sorry for the inconsistency, but then if j is greater than I, so if m is greater than n, then I want to take the covariance sum, and I'm going to add our value here, which is the exponential exponent and minus kappa times by u minus t. And then I've got our variance q, and essentially all that is our variance intervals at that particular time interval I, or t in this case, whichever indexing method you want to use. Now I'm just going to calculate the sum of those variance intervals, and then I've already calculated the sum of the covariance, and I just need to multiply it by 2 and then add it to the sum. Now, in reality, how am I actually going to apply both of these risk neutral measures? Well, I'm going to come up with another function. We're going to call it risk neutral. I'm going to read in our trading dates that we're interested in. I'm going to read in the T-bar parameters for our average temperature model, our volatility model that we've got, so our B-spline model. I've got the first ordinal, which defines the time that our model actually starts from. And then I've got lambda, our risk neutral constant, and then kappa, which I've defined as our model that we've actually defined using the physical probability measure. Now, essentially all I'm doing is that I'm actually applying the model that we've got to our specific trading dates that we're reading in for our risk neutral, our specific circumstances, so winter, and then I'm calculating our Monte Carlo temperatures only just to get the average temperatures for each day. So I'm building up this data frame so that I can actually get the average temperatures as defined by our modified Ornstein-Uhlenbeck process. So I'm going to pass that in for our risk neutral mean and our risk neutral var, and then we're going to return our risk neutral mean and our risk neutral var given our model and circumstances of the trading dates that we're interested in. Now that we've got our risk neutral mu and our risk neutral var, how can we actually apply that in a closed form solution? Well, essentially using the fundamental theorem of asset pricing, we've got the following formula. So we've got our expectation under the risk neutral dynamics is equal to our payoff divided by our bank account, our risk-free asset, given our filtration T. Now, if we take this BT to the other side, which is our risk-free bank account, our discount rate, we have actually applied where we've got our discount rate, our risk-free process is actually constant over time. So here we can just apply our call option payoff, and that's going to be, again, for our call, we've got the alpha, which is the tick of each heating degree day, times by the degree days minus K, and then it's obviously the max function. So we've got our call price is equal to the discount rate times by this expectation. Because alpha is a constant, we can take that to the left-hand side, and then we can apply the integral over this domain space in the risk neutral space. So what we have is we've got this function of heating degree days under the risk neutral probability measure, so our PDF, and we've got our integral from K all the way to infinity. So because this is a very easy payoff function to define, essentially what we can do is use the fact that this is a normally distributed variable under the risk neutral probability measure. We can actually get this in a closed form solution, much like the Black-Scholes model for European options. So here we've got ZT is equal to K minus mu T divided by sigma T. So that's just the square root of our variance process that we calculated before, where this theta is the CDF of the normal distribution. So we have our call option, and for the put, we can do the exact same process. And when you break it out, you get this formula here. So now let's apply both of those formulas using Python. So again, only for a winter option can you use this scenario. We've got our trading dates, our risk neutral, our risk-free rate. We've got our alpha, which is that tick, dollar per tick. We've got our strike, our tail, and then our option type. We've also got lambda, which we're going to define our new risk neutral parameter, which is equal to 0 by default. So let's evaluate the fair value of a temperature option in winter based on a heating degree day only if the physical probability of the average temperature exceeds the T-ref 18 degrees and is close to 0. So not really the case in Australia, but you can use this in other places. Nevertheless, let's do it for an Australian option. First thing we're going to do, let's calculate our risk neutral mu and our risk neutral variance. How do we get that? Well, all I need to do now is apply our risk neutral function with our trading dates, T-bar parameters for our model, our volatility, and then our volatility model and our first ordinal and lambda. Once I've got that, all I need to do is come up with some functions to actually make this calculation a little bit more tangible in Python. I'm going to come up with our discount rate. So exponential minus r times tau. I've got our volatility risk neutral, which is just the square root of our variance. And then I've got zt, which is k minus the mu divided by our volatility. And then our exponent, our first exponent is going to be numpy exponential minus zt squared divided by 2. And as you can see, that's used in a number of parts in both the put and the call. So for the call, all I need to do is I'm going to go alpha times by the discount rate times by all in brackets, these terms here, mu minus k times by CDF minus zt plus the volatility times by that exponent we calculated before divided by the square root of 2 pi. Now, if it's not a call, then it's a put, and we need the second exponential here. So if I've got the second exponential, what I can do is I can calculate the put in a very similar way. So applying the formula, you get this term here, and I want to return that. What does that look like in real life? Well, essentially, if I'm interested in my trading dates of next winter, June through to August, I can define my trading dates using Panda's date range. I've got my risk-free rate at 5%. I've got a strike of 300, and I've got alpha at $2,500 per tick. So tau is going to be the number of years between that. And as you can see, start date is the 16th of October today, and then the end of the contract is the 31st of August 2023. So the years between the dates is 0.873 years. Now, if we apply all of those variables that we've just defined into the call price and the put price, you get the following using the Black-Scholes approach. Done, easy, closed form solution. You can use that again and again and again. So now we're going to move on to the Monte Carlo valuation methodology. So essentially all we need to do here is calculate the discounted expectation of the payoff under the risk neutral probability measure. So we're going to simulate out these temperatures, and then we're going to calculate the number of resulting heating degree days in the valuation period. Once we've done that, we can then apply the payoff function, get the average, take the expectation, and we'll calculate it. So without further ado, we're going to define the date range again. So again, from July through to August. We've got our number of sims, 10,000, that we're going to define. We've got our volatility model, which is our spline. So now let's define a function to actually compute the Monte Carlo price of a temperature call option. Now, at the previous video, we actually went through how you can simulate the temperatures under a Monte Carlo simulation. So there we get back our temperatures and then our simulation of the temperatures for each day on each of the simulations. We can define the shape, so the number of days n, and the number of simulations by the shape of our array here. Here we're just changing it to an array, and then we can use the numpy sum to calculate the number of heating degree days in that period. So for that, the heating degree days, it's just the maximum between 12, the reference temperature, and our Monte Carlo array of temperatures for all the simulations for all the days. And then we're taking the maximum between that value or 0, calculating, summing them all up, and we get our heating degree days over the entire period for our simulations. Now, essentially what we have then is we're summing on axis 0, so we got it for our heating degree days for each of the simulation periods. Then for a call, I can then take our payoff as alpha times by the maximum between these heating degree days for all those 10,000 simulations minus the strike. And then for a call, I can just do the opposite, K minus the heating degree days. So to calculate the price of the temperature option, all I have to do is then now take the discount factor. So I'm going to multiply the discount factor by the average of those payoffs. So to get the average, I just take the sum and then divide through by the number of simulations, M. Now, out of interest, I'm just going to return the standard error back for our Monte Carlo simulation because I'm interested in that. So I'm just going to apply the formula, the square root of the sum of the difference between the discounted payoffs minus our actual expected value, our temperature option price, all squared. Then I'm going to divide through by m minus 1. And then for the standard error of a Monte Carlo error, all you need to do is then scale it by, you divide by the square root of m. Now I'm going to return back our fair value, C0, and then our standard error. And then I can just print out what it is for the call and the put. And similar before with the strike that we had, then you get the following prices here. Now, there is going to be a difference between using these two approaches, especially when we're considering Australia. Again, why? Because the approximation method of the Black-Scholes approach is not perfect in Australia, because we do have periods during winter where it exceeds the reference-based temperature. That average temperature during winter exceeds 18 degrees. So it's not perfect, but during winter periods in other places, it could be a better way to approximate our temperature option value. Otherwise, please lean upon the Monte Carlo approach under the risk-neutral methodology. So comparing the two methods, all we need to do is we'll check out a whole number of strikes, which just equate to the heating degree days within that winter period, the 3 months. So I'm going to go from 180 through to 500. I'm then going to build up a NumPy array with all our different calls and puts for the two options. Here I'm then going to define a data frame where I'll just call it the call Monte Carlo and then the call as the Black-Scholes approximation approach. And we'll do that for the put as well. Now, if I plot that, you can see here on our diagram that we then have our similarities between the call and then the puts. Now you can see that the put is more closely aligned than the call values. Now, it's obviously a all right approach, but as you saw with in Australia, Sydney, with 5% under the physical probability measure, 5% chance that the average temperature exceeds that reference temperature, maybe the Black-Scholes approach isn't the best one to take. But regardless, it does a pretty good job. Hope you enjoyed this weather derivative series and you learnt a lot about the process of modeling, modifying, using Ito calculus in a practical way, and then being able to apply different methods of interpolation to add in non-linear volatility to your models, and then being able to apply it to actually a practical process. What I'm interested in now is actually using these models to then calculate what some of the risk parameters, so this risk parameter, that risk neutral parameter we have, lambda, and actually calculating lambda based on market traded values in the weather derivative space. So stay tuned for that. Also, I don't want to finish the series because I'm really interested in checking out some rainfall derivatives as well. So if you're interested in sticking around and learning more about quantitative finance, please sign up to the YouTube channel and I'll see you in the next one.